Okay, hello, welcome back. This is 5.3 now, and we're continuing on with mathematical induction and other kind of settings. In particular, divisibility and inequalities. Okay, so the divisibility, not so important, but the inequalities will be super important if you're going to continue studying mathematical concepts like distances and ordered sets. So I don't know. Let's take a look. Okay, so we'll start with divisibility. You can use inductive proofs all over the place, really. I don't know, but they're highly regimented, you know. Anyways, number 9, we want to prove that 7 to the n minus 1 is divisible by 6 for n and z such that n is greater than or equal to 0. Okay, so we're going to do this by induction. First, the inductive step, p of, and we start at 0, is 7 to the 0 minus 1 is divisible by 6. And it's not like the left hand, right hand type proof. Now it doesn't fit that format, you know, so the template kind of changes, but it's similar enough that I'm not going to like rewrite a new template for us. Like you know, if I was going to code everything I would, but I'm not going to bother. So p of 0 is 7 to 0 minus 1 is divisible by 6. We note 7 to the 0 minus 1 is equal to 1 minus 1, which is equal to 0. Furthermore, then, or also, 0 is equal to 6 times 0. So if you remember your definition of divisibility, d divides n if and only if there exists k and the integers such that n is equal to d times k. And that's kind of what we just shown there. Okay, so hence p of 0 is true. Okay, so step 2, the inductive hypothesis. Now we're doing a supposition. So we're supposing k is a payback integer such that k is greater than or equal to 0 and p of k is true. So and 7 to the k minus 1 is divisible by 6. And it's probably best to invoke the definition of divisibility to instantiate kind of an alternate form, right? So in other words, then, 7 to the k minus 1 is equal to 6 times r for some integer r. Okay, so we want to show, obviously, the p of k plus 1 is true, so we want to show, just get that statement out of the way, 7 to the k plus 1 minus 1 is divisible by 6. In other words, again, we kind of talk about this as in terms of the definition. In other words, there exists some other integer, we'll say s, such that 7 to the k plus 1 minus 1 is equal to 6 times s. Okay, so we start on by using this 7 to the k plus 1 minus 1 thing. Okay, so we note that's kind of like starting on the left hand side, but I don't know. We note 7 to the k plus 1 minus 1. And then we're going to do some clever arithmetic manipulations to produce 7 to the k minus 1 inside of this statement. So I can rewrite 7 to the k plus 1 as 7, first off, just by rules of exponents, 7 times 7 to the k minus 1. Note 7 to the k plus 1 is equal to 7 to the k times 7 to the 1. They have like bases, right? You're used to going in the other direction, like a to the x times b to the y is equal to a to the x, or if you have to have the same base, right? So a to the x times a to the y is equal to a to the x plus y. We're just kind of using that formula and going in the other direction. So splitting it up into two like bases based off that exponent. So 7 to the k plus 1 is equal to 7 to the k times 7 to the 1 right here. And then commutative property, you can rewrite that as 7 to the 1 times 7 to the k, which is right here. Okay, so what? Well, now I can rewrite this thing in another clever way. So note this is the same as writing 7 times 7 to the k minus 1 plus 6. Okay. So what exactly did I do? Maybe I can make it a little bit more understandable as to how this works. It's kind of like when you add and subtract something at the same time. So all I did was take the 7 to the k and rewrite it as 7 to the k minus 1. Okay. So what do I have? I have 7 times 7 to the k minus 7. Okay, so maybe it would be okay, so what is this? 7 times 7 to the k minus 7 over here to the side, maybe. And if you immediately add in 7 and then subtract the 1, this statement here is, this is exactly the same as this statement here. Now I'm getting too many circles, right? This is right here. It's very frustrating for me. Okay. What? Well, I can then rewrite this thing. You agree, hopefully, that these two guys are the same. Okay. Negative 7 plus 7 is 0, and then I just negative 7 plus 7 is 0, and then I just get back to 7 times 7 to the k over here minus 1, right? Okay, so what I'm saying is that this is the same as if you factored out a 7, and then you would have 7 to the k minus 1 plus 7 minus 1. Okay, so on the outside of that guy, you're going to put plus 7 minus 1. So it's just a clever way of introducing the p of k expression into what we're doing. So then we could use the inductive hypothesis to kind of get rid of the p of k. All right. So it's just some clever algebra. It's a means to an end, though. Okay, so from the inductive hypothesis, then we can replace that thing I just circled in red with 6 times r. I believe we called it r. And then plus 7 minus 1. 7 minus 1 is 6, right? And then we could factor that 6 out. So we'd have 6 times 7r plus 1, where 7r plus 1 is a product. Where 7r plus 1 is product and sum of integers, and therefore an integer. So this thing is 6 times some integer, which means it's divisible by 6. Hence, it's divisible by 6 by definition of divisibility. So I'm leaving a lot out, but I'm hoping you can follow. Just for the sake of sanity, I don't want to write it all out. And in the homework, you'll be filling in the blanks, so it's not like you won't know how far to go with to avoid jumping to conclusions. A miracle happens, like I showed you in the comic last time, and then all of a sudden, here we are, right? Okay, so anyways, that's the one proof. Let's look at another one. This one is a little more complicated. You want to show that n cubed minus n is divisible by 6 for all n greater than or equal to 0. Alrighty then. So we do a proof by induction again. So we note step 1, our basis step, p of 1 is the fact that 1 cubed minus 1 is divisible by 6. Right? We note, and you want to avoid starting sentences with numbers. That's bad English. So we note 1 cubed minus 1 is equal to 1 minus 1, which is equal to 0. Also then, just like in the last problem, 0 is equal to 6 times 0, so p of 1 holds by definition of divisibility. Okay. Then the inductive step, we're supposing k is a payback integer such that k is greater than or equal to 0 and p of k is true. So k cubed minus k is divisible by 6. Let me just write 6 divides k cubed minus 6 instead of writing that out in English. In other words, now we're going to kind of invoke the definition to make it easier to stomach. In other words, k cubed minus k. In other words, there exists some r in the integers such that k cubed minus k is equal to 6 times r. Okay. We want to show that 6 then divides k plus 1 cubed minus k plus 1. Okay. In other words, and then again we have invoked the definition. There exists some s in the integers such that k plus 1 cubed minus k plus 1 is equal to 6 times s, where that thing is my cursive s. Okay, some people write s like that. I write it cursively like that. Okay. Then we note this, what the heck this k plus 1 cubed thing is, minus k plus 1. So cubing out the k plus 1 cubed is, you FOIL and then distribute. So k cubed plus 3k squared plus 3k plus 1 minus k minus 1. And then that equals, what does that equal? K cubed. And I kind of want to get this inductive hypothesis invoked, so I need like a k cubed minus k somehow. Anyways, let's see what the other stuff is. These ones will cancel. I'll have a, I don't know, plus, losing my place, plus 3k. Okay, so just plus 3k squared plus 2k. All right, and then this will equal, and I need to invoke this k cubed minus k thing somehow. So a bit of tricky again. So I need k cubed minus k in here. So immediately add in another k and then plus 3k squared plus 2k, and then that'll equal k cubed minus k plus 3k squared plus 3k. And then I can use the inductive hypothesis to at least rewrite the k cubed minus k part as 6 times, what was our first variable, r. And then the second part, and this is, you have to be a little bit clever to kind of see this, 3 times k plus 1. Okay. Now the clever part is noting that these two terms here, inside of those, either k or k plus 1 has to be even. Okay, either k or k plus 1 is even. And then you also note, so we kind of do a little proof to the side here. From there, an even times an odd is even, right? I mean, that kind of just says it in itself, because k or k plus 1, one has to be even. If one is even, then the other one is odd. The other case, if one is odd, then the other one is even. In another case, you have an even times an odd, and we learned that that is equal to an even. Okay, so we can replace all of that stuff. Let me circle it in a different color. We can replace all of this junk with 2 times some integer. Okay, so this will equal 6 times r plus 3 times 2 times some other integer. Let's say qrs, let's call it q, where q is some number in the integers. Because by the definition of even numbers, we're allowed to do that. Okay, so now we can rewrite this then as 6r plus 6q, and then we can factor out the 6, and we got it, right? So that'll equal 6 times r plus q, where r plus q is a sum of integers and therefore an integer. Hence, this k plus 1 cubed minus k plus 1 is 6 times some integer, and hence, let me just jump to the conclusion. Hence, I know I'm not supposed to do that, but hence 6 divides the k plus 1 cubed minus k plus 1 by definition of divisibility. Okay. I'm allowed to jump to conclusions, you're not. It's like when your parents tell you like, we're allowed to smoke but you're not, you know. So that's sort of hypocritical. I'm a hypocrite. Okay, deal with it. It's the power of making lecture videos. I don't have anybody talking back to me. Anyways, there's that. Okay, divisibility, great. Okay, if I take number theory, I'll try to remember that stuff, right? Okay, anyways, inequalities. I think this is definitely a deficit in the math education here in our country, working with inequalities. We take all kinds of junk for granted. For example, if a and b are in the positive integers, and let's say, let's put in some other ones too, right? So a, b, maybe c comma d are in the positive integers, and c is less than d, then we can multiply both sides by a, right? And just things like that. So maybe we don't need 3 variables, just a, c, and d. Then we can multiply a on both sides, and the inequality still holds, right? Okay, so just little factoids like that. Of course, that won't work if you multiply by a negative number. You know, you don't have time to play around a lot with inequalities. So, like I said, some things are just taken. You take them. You don't even think about them. So one thing that comes up in like calculus class, you're trying to show that the relationship between 1 over k plus 1 and 1 all over k plus k, right? And we're supposing that k is greater than 1. Okay, so if k is greater than 1, then this denominator will be greater than this denominator, and then this inequality, sorry, it's the other way around, right? The other way around. Then this equality will hold. And that's kind of more of a direct proof type thing. It's not an induction or anything like that. So if this denominator is bigger, that makes it smaller, right? How would I prove that, like in a direct type proof? I would have to start with this k greater than 1. So suppose k is some positive integer such that k is greater than 1, some payback integer such that k is greater than 1. Note then that, so how would this work, right? We can add 1 to both sides or something like that. We could say k plus 1. How would this work? K plus 1 is, I want to start with that inequality. Sorry, I should have prepared this a little better. So I have 1 less than k, right? So note 1 is less than k, and then I want to use kind of adding things to both sides. So if I add a k to both sides, that would be k plus 1 is less than k plus k. So that's no news there, nothing to write home about. Then what can I do? Well, what is well, I did that wrong, right? So no, I added k to both sides. That's fine. Is that exactly what I wanted to show? Yeah, that's kind of what I wanted to show up there. Then you could divide, both of these are greater than 0. So you could divide both sides by k plus 1, and you get 1 less than k plus k all over k plus 1. And then you could divide both sides by k plus k, and you get 1 all over k plus k is less than 1 over k plus 1. And of course, that was the inequality from up there that we were trying to show. Right? So in calculus, they kind of expect you to be able to do that intuitively. So this would end up equaling 1 over 2k, and then we could talk about the sums. This would be like a comparison test in calculus. Okay. I don't know. Some other obvious facts that I'm going to use in this next proof. So if something is true, like k is greater than 3, so it's just obvious stuff, you know, that you have to invoke in order to get your proofs to work. Then 3 times k is going to be less than or equal to k times k. And I think it's hopefully obvious as to why that's true, right? You're just multiplying both sides of this inequality by k, and you could pull that off because k is greater than 3 and therefore greater than or equal to 3 and therefore greater than 0. So when you multiply both sides by the inequality, it won't change the direction of the inequality. Okay. Another fact: if k is greater than or equal to 1, then I can kind of do what I did on over here. I could say add k to both sides, right? So changing sides, 1 less than or equal to k, adding k to both sides, k plus 1 is less than or equal to k plus k, which is equal to 2k. So it's just, I don't know how to explain it. It's just these weird kind of taken for granted baloney factoids that we use that I don't know. Let's try number 19. Hopefully it'll give you an idea where I'm headed with all this junk. I'm trying to prove n squared is less than 2 to the n for all n, greater than or equal to 5. Okay, and I'm going to do this by induction. So proof by induction, and I'm going to start out with my inductive step saying P of 1 is, or P of 5, you have to start at 5, right? So P of 5 is 5 squared less than 2 to the 5th. We note 5 squared is equal to 25. Also then 2 to the 5th is equal to 32. Hence P of 5 holds because 25 is less than 32. Okay, so hence P of 5 holds. Okay, now we want to go to the inductive part. And what are we doing here? So suppose K is a payback integer such that K is greater than or equal to 5 and P of K holds. So what do we got? K to the second power is less than 2 to the K, right? Okay, so we want to show that K plus 1 squared is less than 2 to the K plus 1. And we're going to be using these kind of obvious factoids of just building inequalities using basic axioms and facts about numbers. Okay? So we want to show that this is true. Okay, so we note the left-hand side here. We note K plus 1 squared is exactly the same as K squared plus 2K plus 1. That's just foiling. And then we could start invoking some of those inequalities from above that I kind of built. So this is the same as, this is less than K squared plus 2K plus K, because K is said to be greater than 5, greater than or equal to 5. And if given that K is greater than or equal to 5, that means that well, because 5 is greater than 1, K must be greater than 1. Okay, so we can augment this statement by just replacing the 1 with a K. You can kind of think of it, it makes it bigger, right? Okay, so then that will be equal to K squared plus 3 times K. All right, and then again I could use sort of the above factoids. This will be less than K squared plus K again is greater than 5, so 3 times K is going to be less than K times K, okay, which will be K squared plus K squared, which will be equal to 2K squared. And why are we pulling all this baloney? It's to invoke the inductive hypothesis here. So K squared is less than 2 to the K. So this thing will be less than 2 times 2 to the K. All right. And of course that equals then, if you just add the exponents of the like bases, 2 to the 1 times 2 to the K is 2 to the 1 plus K, or in other words 2 to the K plus 1, which is what we wanted to show. So it's just some tricky algebra, and once you kind of see it and maybe you go through 1 or 2 of these, they're pretty easy. It's just a matter of manipulating things and using inequalities in this kind of new way to build chains connecting to things that you want. Okay. All right, so anyways, there's that baloney. Now getting on to then sequences. We want to find closed forms for recursively defined sequences. So for example 5.3.3 in the book, they're defining a sequence to be, so the sequence a sub 1, a sub 2, a sub 3, comma, dot, 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 to start with a sub 1 equaling 2, and then they give you a recursive definition. A sub k equals 5 times a sub k minus 1 for all ints k greater than or equal to 2. Okay, this stuff is basically then going to become definitions that you could use throughout the proof. It's given material. Okay, so you use it however you want in the body of the proof. Okay, so anyways, in the book part A, they just want you to write out the first 4 terms. Okay, this is a geometric sequence, I believe. So we have formulas for this. You may remember them from pre-calc, but let's just use the recursive definition. So A1 is 2. A2, from this recursive definition here, is 5 times the previous number, which is A1. So this will be 5 times A sub 1. Ugh, get rid of that color, which is 5 times 2, which is 10. Okay. And then A sub 3 will be 5 times the previous A sub 2, right? So that's 5 times 10, which is 50. And then A sub 4 is equal to 5 times 50, which is equal to 250. Okay, so this could be quite time consuming, especially if you need like A 3 million to have to go through there and build it one by one, because you can only know A 3 million if you know the one right before it. So ideally, we would want some sort of formula that can give me a particular A sub n term. Okay, and we're going to be given that formula in the book, and we want to prove that to be true. So we're going to be given A sub n equals 2 times 5 to the n minus 1, and we want to prove that to be true. So what is the power of this formula? Well, it's a predictive formula such that you don't need to know anything except the index that you're using. So for example, to find A sub 4, I don't need to know A sub 3. I can just plug 4 into my equation. So 2 times 5 to the 4 minus 1 is 2 times 5 to the 3, which is 2 times 125. 5 cubed is 125. And then 2 times 125 is 250. Okay, so I didn't need to build up to it with this formula. Okay, so that's what we want to do. We want to prove that that formula is kind of the closed form for this recursively defined sequence. Okay, so here we go. Part B, we're proving A sub n is equal to 2 times 5 to the n minus 1 for n greater than or equal to 1. Okie dokie. So first, again, we prove by induction. Okay, I'll just write proof by end. The basis step, P of 1, is that what is it? A sub 1 equals 2 times 5 to the 1 minus 1. Okay, the left-hand side, A sub 1 is equal, and this is where you invoke the definition back here. So A sub 1, we said in our definition, was equal to 2. Okay, so I come back down here, and I write 2. Next, 2 times 5 to the 1 minus 1 is equal to 2 times 5 to the 0, which is equal to 2 times 1, which is equal to 2 as well. Hence, left-hand side is right-hand side, and P of 1 is true. To the inductive step. So suppose K is a particular but arbitrarily chosen integer such that K is greater than or equal to 1, and A sub K is equal to 2 times 5 to the K minus 1, right? We want to show that A sub K plus 1 is equal to 2 times 5 to the K plus 1 minus 1, which will just end up being 2 times 5 to the K. Okay, you start on the right-hand side and note what is A sub K plus 1. Okay, and again, we're going to zip back to our definition, and this time we go with the red definition. So we're going to plug in K plus 1 wherever we see K. So we'll end up with A sub K plus 1 equals 5 times A sub K plus 1 minus 1. Okay, so I just plugged in, again, K plus 1 in for K in here. Okay, so then this thing equals 5 times A sub k, and then I can use the inductive hypothesis. The inductive hypothesis says that a sub k is equal to 2 times 5 to the k minus 1. And then like bases add exponents, right? So 5 to the 1 times 5 to the k minus 1 is 5 to the k minus 1 plus 1, which is 5 to the k. So I have 2 times 5 to the k. And lo and behold, that's what we were trying to show, right? So that's this thing right here, okay, which is what we wanted to show. Okay, so the formula is true, it works by induction, blah, blah, blah. Okay, so leave it at that. And we'll see you next time, okay? Okay, see you next time.